Hi everyone and welcome. In today's video, we will discuss ordered fields. The point of today's video is actually to cover the basic rules and properties of the set of rational numbers and the set of real numbers that you're probably familiar with from elementary school, but we're going to take a look at them in much more rigor and in a precise way. And in doing so, we will begin to understand the similarities between the set of rational numbers and the set of real numbers, and we will see what kind of mathematical objects they are. And so what we will find is that they are something called ordered fields. And ordered fields are basically number systems in which we can add, subtract, multiply, and divide, and also compare numbers in a very nice and consistent and logical way, and something that we have been taking for granted and doing since elementary school. So we're going to cover all of this, but in a more precise and rigorous manner. And so to begin, let's begin by understanding what is a binary operation on a set. Given a set F and two elements, let's call them X and Y, which are both members of the set F, we can define an operation on the set F, and it's just going to be a function, a mapping, that takes the ordered pair X, Y to a third element also inside of F. Now there's two things important to note here. Notice the keyword ordered pair, right? Because this is a general operation. So an operation that you might be familiar with is addition, and usually addition commutes. In other words, x plus y is equal to y plus x. But this is a very general definition to capture a wide range of operations, and so the order might actually matter. And as an example that you might be familiar with is matrix multiplication. So if you were to define the operation as matrix multiplication, the order in which you multiply matrices does matter. So that's why ordered pair is important. And the other point is that the operation never leaves the set F, right? So when I take two matrices and I multiply them together, I get another matrix. And so it's very important to keep this in mind, that the operation will always map back into the original set. And on the side here, I have some explicit ways of how we can write operations. So as I mentioned, they just happen to be functions. And so you can give them names like f, g, h, but you can also give them special notations. So for example, addition and multiplication are very common operations, and so as a result, instead of formally defining the plus operation going from the set F back into itself as plus x, y, right, it's a little bit unintuitive and we don't really write plus like this. What we instead write is simply x plus y. And so whenever we write x plus y, that really means this notation here. And so from now on, we will actually just continue with writing x plus y, but know in the back of our heads that this is what we really mean. It's this operation defined on a set back into itself, and this is one other way you could write it. Now that we understand operations, we're ready to begin to understand ordered fields. So an ordered field, let's call it F, is just a set that is equipped with two operations: an addition operation, which we denote by x plus y, and a multiplication operation, which we denote by x dot y, or x times y. And so these operations satisfy the definition above. Additionally, an ordered field is also equipped with an ordering relation, which we denote with this less than or equal to. And so this set F must satisfy the following 10 axioms. So real quick, let's understand, what do I mean by the term axiom? In case you have not come across this term yet in your mathematical career, an axiom is a statement in mathematics that we can assume. And you might say, well, how can we assume something in math, right? It's supposed to be something very rigorous and formal. We should prove everything, right? But we need a starting point. And so these axioms, or these assumptions, are supposed to be very basic mathematical statements that we take for granted or we can assume. And then the goal is to actually build theory on top of these axioms or these statements. And so one way I like to think of mathematics is actually as a game. And in this game, what you do is you define a set of statements or a set of assumptions, and then you see how far you can get from these set of assumptions. You see what results follow and what things you can derive and how far you can get. And so that's what these axioms are. And so now let's briefly go over each of these 10 axioms, and you will see that they're actually very basic statements that we've already been assuming since elementary school. So the first axiom is the commutative axiom, and this is the axiom that deals with the order of operations. So it allows us to add and multiply in whatever order we like. In other words, x plus y is equal to y plus x, and x times y is equal to y times x for any two members of the set F. The next axiom is the associative axiom, and this allows us to re-bracket terms whenever we're doing operations. In other words, I can first do x plus y and then add z, and that will be equal to if I first did y plus z and then I added x. And similarly with multiplication, the next axiom deals with identities. And so in ordered fields, there will always be two special elements, a 0 and a 1. So ordered fields can never be empty. They must have at least two elements, a 0 and a 1. And these 0 and 1 have the following properties. So first of all, 0 must be different from 1. These are two unique elements, two distinct or different elements. And they act as you would expect. So whenever I add 0 to an element, it does nothing, right? And when I multiply by 1, it does nothing. And so what these are called are respectively the additive identity and the multiplicative identity of this field. And another thing I would like to mention here is that these definitions are very general and abstract. So although I wrote 0 and 1 here, the set F doesn't have to be a set of numbers. It could be a set of functions, or it could be a set of matrices. And so the elements that act as 0 or 1 may not actually be the numbers 0 and 1, but they will act like a 0 and a 1 because they will satisfy these properties. The next axiom is a very useful axiom that helps us solve equations, and it's the inverse axiom. So given any element in my field, there will be a negative x, so that when I add them together, they cancel out to give me 0, or the additive identity. And moreover, if x happens to be non-zero, then you can always find the reciprocal of it, right? We denote by this multiplicative inverse, x to the power of -1, so that when I multiply x and its multiplicative inverse, I get 1, or the multiplicative identity. And the last algebraic axiom is the distributive property. So when I have x multiplied by y plus z, I can actually distribute the x, right? So I can get x, y plus xz. And so this axiom is a little bit special because it captures how these two operations play with each other, right? How the multiplication distributes over addition. The next 5 axioms deal with the ordering. So for any two elements in my field, at least one of the following statements must be true. Either x is less than or equal to y, or y is less than or equal to x. In other words, I should be able to compare numbers, right? I should be able to know which one is bigger or smaller. The next axiom states that if x is less than or equal to y, and y is less than or equal to x, then it must be the case that x is equal to y. They must be the same element of the field. The next ordering axiom refers to the transitive property, something that we have been using for quite some time since elementary school, which is that if x is less than or equal to y, and y is less than or equal to z, then we can also say that x must be less than or equal to z. The next ordering axiom says that if y is less than or equal to z, then if I was to add x to both sides of this inequality, the inequality will still be preserved. And this axiom is very helpful for manipulating inequalities, right? If you're given some inequality, I should be able to add on both sides the same number, and still the inequality should be preserved. And finally, the last ordering axiom is that if x is non-negative and y is non-negative, then their product is also non-negative. And so now, taking a quick step back, for a set F to be an ordered field, it must satisfy all 10 of these axioms. Okay, it must satisfy all 10 of these axioms along with the two operations, addition and multiplication. They must be valid operations that satisfy this definition. Then we can say that F is an ordered field. Just for those that are interested, there's actually a distinction between an ordered field and a field. So a field is actually a little bit weaker notion, in which we only need these 5 axioms to be satisfied. But if you also have these extra order properties, then it becomes an ordered field. But in our case, we will just be dealing with ordered fields, and so we will just refer to these as the 10 ordered field axioms moving forward. And now, as you're probably reflecting upon these 10 axioms, these 10 statements that we are going to be taking for granted, you might question, how come we're missing other properties? Like, for example, what if I do x multiplied by 0, right? X times 0 should be 0. I know I've been using that fact since elementary school. Why isn't that listed on this list, right? Or for example, -1 times -1 is equal to 1, right? That's a basic fact that we've all been using forever. And so how come that is not listed on this list? And so it turns out that from these 10 axioms, we can actually derive all those familiar facts that you know. And so we want to keep this list as tidy as possible. We want to keep it as minimal as possible. We can actually prove all the basic properties that you have been using since elementary school from these axioms. So for example, the difference of squares formula, where you have a squared minus b squared factors nicely into a minus b times a plus b, well, that can be derived from these 10 axioms. You can also derive x times 0 is equal to 0 for any element of the field. And you can also prove things like -1 times -1 is equal to +1 using these 10 axioms. And so we will see some examples of that later on in this video. Next, I would like to look at some non-examples and examples of ordered fields. So for some non-examples, the set of natural numbers is not a field. Why not? Because it does not satisfy the additive inverses. So axiom F4 is not satisfied. So if I have, for example, the number 17 is a natural number, but it has no additive inverse, right? There does not exist a -17 in the field, so that when I add them together, I get 0. So therefore, the set of natural numbers does not form a field. It does not form an ordered field. Similarly, the set of integers is also not a field. This time, it does have additive inverses, right? For example, 17 has -17, but this time there are no multiplicative inverses. So the number 17 is an integer, but it has no multiplicative inverse, right? So 17 is non-zero, but there does not exist a multiplicative inverse for 17, so that when I multiply 17 by its multiplicative inverse, I get back to 1. And that multiplicative inverse in this case would be actually 1 over 17, right? So that's not an element of this set, and so the set of integers does not satisfy axiom F4. Let's look at this next example, where we have the closed interval from -1 to 1. And this one is a little bit more tricky, because if you were to run through these properties, you will see that most of them are actually satisfied. But remember that in addition to these 10 axioms, we also have these two operations, right? And these two operations satisfy the following definition. And I told you one of the important points about this operation is that you can never leave the set, right? Whenever you operate on two elements of this field, the result should also be in the field. But now going back to this set, let's pick, for example, 1.5, right? These are both elements of this set, but when I, for example, add them together, well, then I get 1.5, right? Which leaves this set. And so in this case, addition is actually not well defined. The proper term for this is that this set is not closed under addition, and so it cannot be a field. Now let's take a look at some examples of fields, of ordered fields specifically. So the whole point of this video is to realize that the set of rational numbers and the set of real numbers, they're both ordered fields. They both have valid addition and multiplication operations and ordering relations, and they satisfy all 10 of these axioms. You can go through and pause the video and convince yourself that indeed all 10 of these axioms are fulfilled by both of these sets. Now next, I would like to actually show you the power of these 10 axioms. I would like to convince you that from these 10 axioms, we can actually prove all the familiar and basic properties that you have been using since elementary school. The first problem that we are going to work on is that if f happens to be some ordered field, then we're going to prove that additive inverses and multiplicative inverses are unique. So if I just go back up to the definition, you see that when we were talking about the inverses axiom, it said that given an element of the field, there is an additive inverse and there is an multiplicative inverse, right? But there could be multiple. There could be multiple. It just says there exists one. It doesn't say there exists a unique one. So you have to be very careful when you read these mathematical statements. But what we will show is that indeed that inside of an ordered field, additive inverses and multiplicative inverses are unique. And so let's take a look at how a proof like this goes. So we will let x be an arbitrary element of the field. And we can do this because, like I mentioned, ordered fields are always non-empty. At the very least, they have a 0 and they have a 1. So now let's clearly understand what we're trying to show. Let's begin by proving that additive inverses are unique. And to do this, what we will do is actually suppose that we have two additive inverses of x, right? So x is some arbitrary element in my field, and I will let y and z be two additive inverses of x. And what my goal is to show that actually y and z are exactly equal. So that's what my goal is. If we do that, then we will be completed with this proof. So what does it mean for y and z to be additive inverses of x? Well, it means that if I do x plus y, I get 0. and if I do x plus z, I get 0, which is the additive identity, right? And so what I want to show is y equaling z. So now let's start with y, and what I want to do is somehow manipulate this so that in the end we just get z, which will show that y equals z. For reference, I have placed all the axioms we will be needing for this proof on the right here, so you can reference them. And on the side, I will also refer to what property is being used. And so you can pause the video and actually refer to the actual property and make sure you understand why that's being used. So now let's begin with y. There's not much to work with here, right? We just have y. But let's add in the additive identity, which does nothing. But now what we can do is actually replace this 0 with something we have, right? We know that x and z are additive inverses, so when I add them I get 0. So I can replace 0 with x plus z. Next, what we're going to do is actually re-bracket the terms, right? And this is the associative property, F2. This allows us to re-bracket the terms as follows. Next, you might see that y plus z is just 0, right, by this property. But I would actually tell you to be a little bit cautious here because we have to be very careful and precise. This statement says that x plus y is 0, not y plus x is 0, right? But in this case you would be right because in fields the addition operation is commutative. So just to be more explicit, what we can first do is actually apply the commutative property here to rewrite this as x plus y, and then we can go ahead and apply the inverses property, which is this equation here, and write 0. So just to be a little bit more precise and careful here, I would encourage you to also work like this. And again, over here we have 0 plus z, right? And notice I don't simplify this straight to 0 because the axiom is written in a different way. Because if we take a look at axiom F3, which I want to apply, it's written as x plus 0, right? Not 0 plus x. So just to be very careful here, we are going to first apply the commutative property to reorder the terms as z plus 0, and then we can finally apply F3, which is the identities axiom, to just get z. And in the end, we ended up showing that if there are two additive inverses of x, then they must be actually the same number, right? Y is equal to z. Next, let's show that multiplicative inverses are unique. And at this point, I would actually highly encourage you to pause the video and try proving this yourself, because the proof is very similar, so it will be a good indication if you are following along or you understand how to apply these axioms carefully. And I want you to be very careful, just like how I was in my steps, and see if you can come with a solution. And then you can continue the video and I will show you the solution. Okay, so hopefully you gave that problem an attempt, but in order to prove this one, we have to make an extra assumption that x that we selected above is actually non-zero, because in the inverses exist axiom, F4, you can see that for multiplicative inverses to exist, x must be non-zero. So we'll just further suppose that x is non-zero, right? If x is non-zero, we'll show that indeed multiplicative inverses are unique. And so it's a very similar flavor proof. We will suppose that y and z are two multiplicative inverses of x. And our goal is to show that y is actually equal to z, right? They're actually the same multiplicative inverse. And so what does it mean for y and z to be multiplicative inverses of x? Well, that means that when I do x times y, I get 1. And when I do x times z, I get 1, right? The multiplicative identity. And so the same idea here, we start with y and we sort of multiply by 1, which does nothing by this identities axiom F3. And then this allows us to actually expand 1. So instead of 1, I can replace this, for example, with x times z, which allows us to introduce the z into the equation now, right? And now the idea is to basically group the yx together and just cancel that out so that we're just left with z. And so I'll run through these steps a little bit more quicker because they're very similar to the previous problem, but we will regroup the y and x together, and then we can use the commutative property to reorder like this. And then we know that x times y, they're multiplicative inverses, so they cancel out and they just give the multiplicative identity, which is 1. And then just to be careful again, let's apply the commutative property here to get z times 1. And again, since 1 is an identity, when we multiply by it, it does nothing, so we just get z. Let's do 2 more problems just to make sure you're really getting the hang of this. So in this problem, let f be an ordered field, and we will prove that x times 0 is equal to 0. And so again, this is a very obvious property, something that we have been taking for granted and have been using for a very long time, but let's actually formally prove it from the ordered field axioms. So let X be an arbitrary element of the field, and then according to the identities axiom, there is a special element 0 in the field, right? Now let's consider the multiplication operation applied to X and 0. And my goal is to manipulate this so that in the end I end up getting 0. And that will show that X times 0 is equal to 0. And so as it goes with most of these proofs, what you start with here is not much to work with. And so what we would do is actually add a 0 and then expand that out. So if we add 0 here, by the identities axiom, this will preserve the equality. And then what we can do is actually replace this 0 with a clever 0. We know that X is an element of the field, 0 is an element of the field. So when I operate on these two elements, I will get a third element that's also a member of the field. And so it should have an inverse. It should have an additive inverse. And that's what allows me to write this, that X times 0 plus its additive inverse is exactly 0. Next, we will regroup the terms so that we place the brackets on the first two terms. And this is done by the associative axiom. Next, we will apply the distributive axiom to pull out an X from these two terms. And so that will give us X times 0 plus 0. And the far right term will just come along for the right here. Now doing this allows us to simplify a bit, because 0 plus 0 was just 0, right? This is by the identities axiom. And finally, check this out. We have X times 0 plus its additive inverse, right? So by the inverses axiom, these must cancel out and give us exactly 0. And this proves the result. We have shown that X times 0 is equal to 0 for all elements in my field F. Finally, let's take a look at one last problem. In this problem, let F be an ordered field, and we will prove that X times -1 is equal to minus X for all elements in the field. So let X be an arbitrary element of my field. Well then, according to the identities axiom, there should be a special element 1, the multiplicative identity 1, inside my field. Okay, well then according to F4, which is the inverses axiom, this element should have an additive inverse, namely -1. This must exist and must be an element of my field F as well. Now the approach for this proof is actually a little bit different. I will not start with one side, X times -1, and show that it equals the right hand side. I mean, you could do that, but here we can be a little bit more efficient and quicker by using some of the results that we have already proved. And I wanted to do this because I want to show you that once you start proving and slowly building these basic properties one by one, your toolbox gets larger. And so it becomes much easier to prove even more identities and more basic results that you're familiar with. Let's understand what we're being asked to prove here. So we are asked to prove that for any element of the field X, the additive inverse must be this, right? And so what we can do is start with actually this equation, right? If I start with this equation here and I have X, and then over here if I can show that this is equal to X times -1, then I can conclude that this X times -1 is actually minus X. And so that's what we are going to do. We are going to start with 0. And then we're going to use the previous result to write this as X times 0. And then we are going to expand the 0 here to write that as 1 plus -1. That's by the inverses axiom. And then we're going to apply the distributive property to distribute the X across this to get X times 1 plus X times -1. And then we're going to apply the identities axiom to this first term here, right? Whenever I multiply by the multiplicative identity, which is 1, it does nothing. So this is just X. And now I want you to consider what we have here. We have X plus something equaling 0. Does that remind you of anything? It should remind you of this inverses axiom, right? X plus something equals 0. So what this implies is that this something here, what we're looking at here, this must be the additive inverse of X. This term X times -1 is the additive inverse of X. That is, it's equal to minus X. And so that proves this result. And I hope you can see from those 10 ordered field axioms, we can actually start building and deriving basic results that we have been using since elementary school. And the more results we prove, the more we add to our toolbox, and the easier it becomes to prove new results. And the last thing I would like to mention is that if this video felt a little bit abstract or very technical, or maybe even somewhat useless, because why are we spending time proving, for example, x times 0 is equal to 0, then don't worry, because in this course we will actually not be spending a lot of time proving field properties from scratch, and that's not something that is expected of you. The proofs in this course will actually be very different from the proofs we have done here. The main point of this video is that the set of rational numbers and the set of real numbers are very nice. They're very well-behaved number systems where all the arithmetic and the inequality manipulations that you have been doing since elementary school, well, they just work. And the reason they work is because they satisfy the field axiom. And so I just wanted to give a little bit more rigor and foundation as to why those manipulations that you have been doing are valid. And so moving forward, we will manipulate equations and inequalities freely without much comment. And that is exactly what we mean when we say the set of real numbers form an ordered field. And so that brings us to the end of this video, where we started to understand what kind of mathematical object the set of real numbers really is. And we saw that it's an ordered field. It's a number system where we can add, subtract, multiply, divide, compare numbers in a very nice, consistent, and logical way, and this is all thanks to the ordered field axioms. But the set of rational numbers, they're also an ordered field. So right now, there is no difference between the set of rational numbers and the set of real numbers, other than the fact that we verbally said that the set of real numbers are supposed to fill in the holes and gaps that the set of rational numbers have. So if the real numbers are truly something more, then they must satisfy additional mathematical properties that actually sets them apart from the set of rational numbers. And so in the next lesson, we will learn about least upper bounds and greatest lower bounds, which will actually help us with that missing piece, which is going to be called the axiom of completeness. And we will see how this new assumption will actually distinguish the set of real numbers from the set of rational numbers, and how it will mathematically and precisely capture filling in the holes and gaps. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.